Welcome everyone to section number 5. Now we finally get to some curve sketching problems. And as the objective says here, right, we're going to be combining some algebra knowledge with our chapter 3 material, right? Increasing, decreasing, concave up, concave down, maxes, mins, all these things, right? And we're going to be able to sketch fairly accurate curves of functions. So that is our goal. You can see here is our first problem, and our goal is only really to do 2 problems for this section. You'll see they're very long problems, but our first one here, and it's broken up into many parts, and we're trying to kind of combine all this information. What is the domain? What are the intercepts? Where are their asymptotes? Increasing, decreasing, critical points, concave up, concave down, and then finally we use all of that information to be able to sketch the function. So a through e kind of combined together, we want to make a sketch of this function f of x. So again, with these things, I would recommend pausing the video. Try to get as far as you can. Maybe you can't get all of these parts, but try to get as many of them as you can, and then I'll go ahead and spoil the surprise for you. So please pause the video, get as far as you can, and then we'll go over the solutions. All right, so let's get to it with part A. What is the domain of our function? Well, usually when we think about domains, we're thinking about what's not in the domain, and right? So you can't divide by 0, for instance, or you can't take the square root of a negative. Things like this. So in this case, well, you can see there's no square roots, there's no division, and so our domain is going to be all real numbers. Any real number makes sense in this case. And in fact, you can see that this is a polynomial. Its degree, I guess, would be, let's see, 1, 2, 3, 4. It's a degree 4 polynomial. And so this is kind of consistent with polynomials. The domain of a polynomial is always all real numbers. Okay, for B, find the x and the y-intercepts. So, okay, if I want to figure out the y-intercept, remember the y-intercept is when x is equal to 0. Remember, another equation for the y-axis is x equals 0. So if you were to plug in x equals 0 into your function, well, let's get out the y value. You'd have f of 0 is equal to 0 times 0 minus 4 cubed, and 0 times anything is going to be 0. So the y-intercept is going to be the point 0, 0. The x-intercept, well, the x-intercept is when y equals 0, or when the function equals 0, right? Another equation for the x-axis, right? Where does it intersect the x-axis would be y equals 0. So if you were to go ahead and set up the equation, 0 is equal to x times x minus 4 cubed, and you try to solve this, well, you see that either x itself is equal to 0 or x is equal to 4. In either of these cases, it would make kind of each one of these terms 0, and 0 times anything would be 0. And so this tells us that there are x-intercepts at 0, 0, which we kind of already knew that from back up here, and at 4, 0, right? When you plug in x equals 4, you get out the y value 0. So that's where the x-intercepts are. Part C, we want to figure about vertical, horizontal, and slant asymptotes. Well, remember, another name for vertical asymptotes are infinite discontinuities. That would require the function to not be continuous. But again, because this is a degree 4 polynomial, the function's always continuous. And therefore, you're not going to have any vertical asymptotes. So I'm just going to go ahead and put no VA, which I use for vertical asymptotes. And again, because it's degree 4 polynomial, you're not going to have any horizontal or slant asymptotes either. So I'm just going to go ahead and put no horizontal asymptotes and no slant asymptotes. So in this case, we don't get any asymptotes. How about part D? Figure out where f is increasing and where it is decreasing. Classify all the critical points. So are they local minimums? Are they local maximums? Are they neither? Right? We want to classify these things. Okay, so here's where we're really diving into the calculus bit, because increasing and decreasing, this has something to do with the derivative. And is the derivative positive or negative? So I need to go ahead and maybe calculate out the derivative of our function here. So the derivative, well, remember our function, it's a product of 2 things. We have x times x minus 4 cubed. And so I'm going to go ahead and use the product rule. So the derivative of the first, so the derivative of x is 1, times the second, plus the first, times the derivative of the second. So the derivative of x minus 4 cubed would be the 3 comes down and you get stuff squared, that x minus 4 squared. So we're leaving the inside alone, and then we multiply by the derivative of the inside. So remember, this is a chain rule thing here. Okay, let's go ahead and simplify this a little bit. So we're going to have x minus 4 cubed plus 3x times x minus 4 squared. Okay, again, I want to know when is this 0 or when is it undefined, right? Because those are where my critical points are. So I want to find the critical points, and that helps me kind of break up the number line and figure out which pieces are increasing and which pieces are decreasing. So, okay, if I want to figure out when this is 0, maybe I want to factor out as much of the common stuff as possible. So I notice that there's an x minus 4 squared, at least in both terms. So x minus 4 squared in both terms. If I was to factor out that from the first term, I would have 1 x minus 4 left over. And from the second term, I'd have this plus 3x remaining. So let's go ahead and simplify one last time. X minus 4 squared, and let's see, we have x plus 3x, that's going to be 4x. And then we still have this minus 4. Okay, so if I want to know when is this 0 or when is it undefined, well, notice that this is just another polynomial, so it's never going to be undefined. There's nowhere that we can divide by 0 or take square roots of negatives or anything like this. So our only hope for critical points are when it's equal to 0. So we have critical points, so I'll do crit points at, let's see, so if x equals 4, then this would be equal to 0. Right? And then finally, if, let's see, x equals 1, right? Because 4 times 1 minus 4. So at x equals 1, there is another critical point. So again, what we're thinking about is when is this undefined or when is it equal to 0? So it's equal to 0 when either x equals 4 or x equals 1. So this gives us our critical points. And remember, critical points are good for kind of breaking up this number line. So we go ahead and we have our number line here. And we break it up at 1 and at 4. And we're going to be plotting information about the first derivative. And so we go ahead and we choose test points, right? So we choose maybe test point of 2 and of 5 and of 0, right? A test point in each one of these intervals. And we try to figure out, is the derivative positive or negative? Because that's what's going to help us determine if the function's increasing or decreasing. All right, so if I was to go ahead and take 0 and plug it into my derivative, right, so here's my derivative. If I was to plug in 0, I would have, let's see, 0 minus 4 squared, and then I would have 0 minus 4. So let's see, when you take negative 4 and you square it, that's going to be positive 16, and you times that by a negative 4 in this case. So positive 16 times negative 4, who cares what the answer is? The big thing is that it's negative. So when you plug in 0, you get out a negative. How about if I was to plug in something like 2? So if I go ahead and delete this stuff, and if I was to plug in something like 2, so 2 minus 4 would be negative 2, and I have to square that. And then if I was to plug in 2 here, I would have 8 minus 4, so that's going to be 4. So negative 2 squared, that's going to be positive 4 times another positive 4. Positive times positive is definitely positive. So greater than 0 here, this is going to be positive. And then how about at 4? So again, let's go ahead and delete this stuff. Or sorry, 4 is my critical point. I want to choose the test point 5. So if I choose the test point 5, so 5 minus 1 will be 1 squared. And then let's see, 20 minus 4, that's going to be 16. Again, who cares what it really is, but it's positive times positive, so that's greater than 0. So this is positive here. And so again, in part D, we want to answer where is it increasing, where is it decreasing, and then classify those critical points. All right, so F is increasing on 1 to 4, and then again from 4 to infinity. F is decreasing on negative infinity all the way up until 1. And then we want to classify those critical points. So x equals 1 is a, let's see, we go from negative, so that's a decreasing, to positive, so that's increasing. So we go from decreasing to increasing, that's going to be a local min. And then x equals 4 is a, and let's see, we go from increasing, to more increasing. So therefore this is neither. So that's how I would write down the classifications there. Okay, and I think we've answered all the questions in part D. Let's go ahead and move on to part E. Part E asks, where is the function concave up and down? Identify all inflection points. And so remember, concavity has something to do with the second derivative. So I need to calculate out the second derivative here. And so that's just me taking the derivative of my first derivative. So I'm going to go ahead and use my most simplified version down here. And so if I take the derivative of this, well, the derivative, again, we can see there's a product of two things. So I'm going to need to use the product rule. We have the derivative of the first. So the 2 comes down, x minus 4. Technically, the derivative of the inside is just 1. So that's the derivative of the first times the second plus the first times the derivative of the second. And there we have our second derivative. Okay, and again, we're going to be asking, where is this equal to 0 or where is it undefined? So maybe I want to go ahead and factor this thing as much as possible. So I may notice that both of these terms have a 2 and an x minus 4. So if I go ahead and factor out a 2 and an x minus 4, well, from my first term, I'm going to have 4x minus 4 left over. And again, if I factor out a 2 and one of the x minus 4s, I'm going to have a 2 left over in this term, and then I'm going to have 1 x minus 4 left over as well. And in fact, we can go ahead and simplify this. Let's distribute that 2. So we're going to have 2x minus 8. Okay, one more line of simplification. So 2x minus 4, and then let's see, we have 4x plus 2x, that's going to be 6x, and then negative 12 and negative 4 and negative 8 gives us negative 12. So again, we're trying to figure out when is this either 0 or undefined, because that's how we're going to break up our number line. So it's undefined nowhere. Again, it's a polynomial. In this case, it's a degree 2 polynomial, so it's never going to be undefined. So we may ask ourselves, right, when is this equal to 0? And that's going to happen at x equals 4, or when, right, 6x minus 12 is equal to 0. And if you were to go ahead and rearrange this, 6x is equal to 12, x would be equal to 2. So this is saying that we want to break up our number line at 2 and at 4. So let me go ahead and draw out our number line here. And I'm going to break it up at 2 and at 4. Now we go ahead and we choose test points. So I'm going to choose maybe 0, 3, and 5. And remember, I'm plugging these things into my second derivative because I'm interested, is the second derivative positive or negative? Because that's what's going to tell me about concavity. So if I was to plug in 0 into my second derivative here, I would have 2 times negative 4 times negative 12. And the big thing is you have 1 positive and 2 negatives. So whatever that answer is, it's going to be greater than 0. So this is positive. Next up, if you plug in a number like 3, you're going to have 2, negative 1. And let's see, 3 times 6 would be 18 minus 12. That's going to be positive 6. And so you have, 2 positives, 1 negative. That's going to be less than 0. So here we have negative. And then finally, if you were to plug in something like 5, you would have 2 times positive 1 times, 30 minus 12. That's going to be 18. And the big thing here is you have 3 positives multiplied together, which is going to give us a positive. So in this case, we have positive, negative, positive. Okay, so again, we're trying to ask about concave up, concave down. Where are there inflection points, things like this? So F is concave up on negative infinity all the way up to 2. Then again, from 4 to infinity. F is concave down on 2 to 4. And then remember, we have inflection points whenever we switch concavity, so long as it's in the domain. So in this case, at 2, it switches from positive to negative, and at 4, it switches from negative to positive. So at x equals 2 and 4, there are inflection points. All right, and finally this last step, use parts A through E to sketch the function. So part F here, let's go ahead and see if we can take all of this information, smash it together, and actually get a decent looking picture for the function. And especially because this is our first time, then we'll go ahead and compare it against a Desmos graph and see how we did. Okay, so if I go back to part A says that, well, the function exists everywhere, right? So its domain is all real numbers. There's no place where we're lifting our pencil or anything like this. It's going to be continuous everywhere. Again, it's a polynomial. Part B says that we get a few points here. So at 0, 0, and at 4, 0, we know that those are points of the function. So let's go ahead and plug 0, 0 here. And let's go ahead and maybe move over 1, 2, 3, 4. And we know that this is going to be a point on the function as well, 4, 0. Okay, moving on to part C. We don't have any asymptotes, so nothing to sketch there. For part D, right, we kind of know something about where it's increasing and decreasing. This is telling us that we should maybe break up this picture at 1 and at 4. So let me go ahead and maybe draw some dotted lines at 1, and then again at 4. And part D says that, right, when you're less than 1, for instance, that the function is decreasing. So over here we have decreasing. And then between 1 and 4, we have increasing. And then we have more increasing at 4. So we have decreasing, increasing, increasing. So I'm just kind of writing things out for right now. And then we'll go ahead and sketch it here in just a second. Okay, how about part E? E talks about the second derivative. It says that we should break it up at 2 and at 4, right? So I also want to break it up maybe right here at 2. Okay, so let's see. When you're less than 2, it's concave up. So this is concave up. And also right here is also concave up. And then between 2 and 4, you're concave down. And then after 4, you're concave up. And remember that we have increasing on this entire bit from 1 to 4. So if you want to, I can maybe specify that it's increasing on this one and it's increasing here. Okay, and finally, a few other points that can be really useful is that we know, for instance, that there are some critical points at 1 and 4. If we can get the y values for those, that would be very useful. So let's go ahead and actually plug those back into our original functions, so 1 and 4. Well, we actually know already at 4 we got out 0. So what happens if you plug in 1 into the original function? So f of 1 is going to be, let's see, 1 times... Let's see, 1 minus 4 would be negative 3 cubed. So negative 3 cubed, well, that's going to be negative 3 times negative 3 times negative 3. That's going to be negative 27. So that's quite a ways down there. So if I was to go back to my graph here, maybe we'll just go ahead, sketch this down a bit more, and say down here there is negative 27 a ways down. So at 1, we get out negative 27. Okay. Likewise, we have special things happening at 4 and at 2. Well, again, at 4, we already know that the y value is 0. But what about at 2? So let's go ahead and get a point there. So at 2, we have f of 2 is equal to 2 times, let's see, 2 minus 4 would be negative 2. And then we cube that. So let's see, we would have 2 times negative 2, negative 2, negative 2. So that's going to be, let's see, negative 8. So this is going to be negative 16 altogether. So again, let's go ahead and make a line here at negative 16. And we know that the function's height there at 2 is negative 16. All right, so something like this. All right, now I think we're all ready to go ahead and start sketching the function. So over here we have decreasing and concave up. So decreasing and concave up. So that's decreasing, but we know that the slope's getting more and more shallow, right? It's concave up, it's starting to kind of turn around, but it's kind of decreasing so much it may be hard to see that. Let's see here if I can draw just a little bit better here. You can really maybe see the concave up. It's hard though. Okay, we have increasing and concave up. So increasing and concave up. So now we're increasing and we're increasing more and more and more. We look like concave up, right? It's above any of its tangent lines. Let me do one more run at this. So I'm going to go ahead and draw it like this maybe. Okay. And then we still have increasing, but it's concave down. So increasing, but concave down. So something like this maybe. Increasing, but concave down. It's below any of its tangent lines. And then finally, we have increasing and concave up. So it kind of switches back. It's still increasing, but now it's concave up. So it looks something like this. Increasing and concave up. All right, so this is what our function will look like based on all of our calculus and kind of algebra knowledge being put together. And so as promised, let's go ahead and take a look at this and verify that indeed this does look like what the actual graph looks like. So here we see, oops, let's go ahead and zoom out. I've graphed x times x minus 4 cubed. We can already see kind of at 4, we're getting a lot of what we predicted. Right, so at 4, kind of goes through this, it levels out, it goes from increasing and concave down to increasing and concave up. All right. Maybe as we zoom out here, we can kind of see the rest of the shape. That, yeah, it goes down to like -27, then it goes up to -16. Here it's decreasing and concave up, decreasing, concave up, all the way to this 1, where it starts becoming increasing and concave up. Then somewhere it switches at 2 to increasing but concave down, and then at 4 it switches to increasing and concave up. So this indeed looks exactly like our picture. Well, maybe not exactly, but very, very similar. And so we can see with our calculus that we can actually do a pretty good job. We don't need calculators or computers or anything like this. Calculus is enough to get a pretty good sketch of these functions. All right, we got one more problem to go. You can see that these are indeed long problems. Again, I recommend pausing this video, trying to get as far as you can, and then I'll go ahead and spoil the surprise. I'll try to be a little bit faster this time around since it's our second problem, but try to get as far as you can, and then I'll talk through the results. All right, so let me go ahead and show you what I have so far. First of all, for the domain, part A, right? Well, here you do have some division, so you have to be worried. We don't want to divide by 0. That happens when x is equal to 2. So x should not be equal to 2 if I don't want to be divided by 0. So therefore, our domain will be everything but 2. So -infinity all the way to 2, and then again from 2 all the way to infinity. For the x and the y-intercepts, well, for the y-intercept, when I plug in x equals 0 back into my original function to try to figure out the y value, well, you'd get 0 minus 0 plus 4, so you have 4 on top, and then 0 minus 2, so you'd have -2 on bottom, and so this gives you out the y value of -2. Okay, how about for x-intercepts? Well, that's when y is equal to 0. So you set this up equal to 0. So this thing equal to 0, you go ahead and you multiply through by the denominator and you try to figure out when is this equal to 0. I sat around and I tried to factor it for a while, but I couldn't. So then I'm going to go ahead and use the quadratic formula. When I use the quadratic formula, right, -b plus or minus b squared minus this 4ac, all in our square root, divided by 2a. Well, when I simplified that down, I got a negative number in my square root, and therefore there are no real places where it crosses this x-axis. So there's no real places where y is equal to 0. So in this case, I have a y-intercept, but I don't have any x-intercepts. And then finally, I started working my way through C. So for vertical asymptotes, I thought at x equals 2, that's probably a vertical asymptote, but it could be a removable discontinuity, so I needed to check. Right? So if I go ahead and I plug in 2, let's see, I would get 2 squared, 4 minus 4 plus 4, right? So that's 4 on top and 0 on bottom, so I have something non-zero divided by 0, so that is indeed a nice vertical asymptote, or infinite discontinuity. Okay, for horizontal asymptotes, we have a degree in the numerator of 2, a degree in the denominator of 1. Since the degree of the numerator is bigger, we know that we're not going to have any horizontal asymptotes. For slant asymptotes, though, This is where I stopped. It requires a little bit of work, right? We need to use our polynomial long division. So we're going to have our x squared minus 2x plus 4, and we're going to be dividing that by x minus 2 to try to figure out if there are any slant asymptotes. So what do I multiply by x in order to get x squared? Well, that's going to be x. So x times x will be x squared. X times negative 2 will be negative 2x. We go ahead and we subtract that away, and let's see, we have 0, and then negative 2x minus negative 2x, so that's going to be negative 2x plus 2x, so that's also going to be 0, and then we bring down the 4, and we can ask ourselves, what do I multiply by x in order to get 4, and that's not going to be a polynomial, and so that's where we stop. All right, so we have a quotient of x, and we have a remainder of 4. And remember, kind of from our last video, that we're going to have a slant asymptote at y equals whatever the quotient is. So y equals x is going to be our slant asymptote in this case. All right, for part D, you may have noticed that we're actually given the derivative and the second derivative. And the claim is, if you kind of search back through the old exams and stuff like this, sometimes this happens. It's meant to speed up the problem so you don't have to take the derivative and the second derivative. And it's also kind of a security measure for grading, right? Because if you mess up the derivative or if you mess up the second derivative, it becomes much harder to grade these things. And to actually determine what people know and don't know. So if we give you this first derivative and second derivative, it's to save a little bit of time, and it's to make sure that we're all looking at the same thing, right? When we're trying to figure out where is it increasing, where is it decreasing, concave up, concave down, etc. All right. So remember, critical points, right? I'm looking at the first derivative now. Critical points are where this is either undefined or when it's equal to 0. So when is this going to be undefined? Well, at x equals 2, right, I'd be dividing by 0. So that's going to be one of my critical points. So let me go ahead and write down for part D. So for crit points, we have x equals 2, it would be undefined. Okay, how about when it's equal to 0? So when it's equal to 0, that's when the numerator is equal to 0. So that's going to be either at x equals 0 or x equals 4. So at x equals 0 or x equals 4, we're also going to have critical points. This is where the derivative is equal to 0. So those are our critical points. That's how we're going to go ahead and break up this number line. I should say critical numbers. So at 0, at 2, and at 4, then we go ahead and we choose test values. So negative 1, 1, 3, 5, things like this. Something in each one of these little smaller intervals or sub-intervals, right? And I'm going to plug those back into the derivative because I'm trying to figure out, is the derivative positive or negative? That's going to tell me if the function's increasing, decreasing, what's going on. And so if I plug negative 1 into my derivative, I'll have negative 1 times, let's see, negative 1 minus 4, that'll be negative 5, divided by negative 1 minus 2, that'll be negative 3 squared. So let's see, I have 2 negatives on top, that'll be positive, 2 negatives on bottom, that's going to be positive. So altogether, we're going to have positive divided by positive, that's going to be positive. So over here, the derivative is positive. Now, how about if I was to plug in 1? If I was to plug in 1, I would have 1 times 1 minus 4 would be negative 3. And then in the denominator, I'd have 1 minus 2, that'd be negative 1, but it needs to be squared. So in the numerator, I have negative. In the denominator, I have positive. So I have negative divided by positive. That's going to be negative. So here we have negative. How about at 3? When I plug in 3, I'm going to have 3 times 3 minus 4 is going to be negative 1. And then in the denominator, I'm going to have 3 minus 2. That's going to be 1 squared. So on the numerator, I'm going to have negative. In the denominator, I'm going to have positive. That's going to be negative altogether. So here we have negative. And then finally at 5. At 5, I'm going to have 5 times 5 minus 4 will be 1, divided by 5 minus 2 will be 3 squared. Everything's positive. Positive numerator, positive denominator, all positive. So here we go, that's positive. Okay, so where is this increasing? Where is it decreasing? Classify the critical points. So F is increasing on negative infinity all the way up to 0, then again from 4 to infinity. F is decreasing on 0 to 2, and then again from 2 to 4, right? That's where the derivative is negative. Okay, critical points, let's classify those things. So at x equals 0, we have, let's see, it switches from increasing, that's a positive derivative, to decreasing. So therefore at 0, we have a local max. How about at x equals 2? Well, at x equals 2, we have to be careful about this one. So this actually is not a critical point. Is not a critical point. And the problem is because 2 here is not in the domain, right? So it is not a point. A point needs an x value and a y value, right? So, but when you try to go find a y value, you're going to have trouble because when you try to plugging that in, you're not going to get out a real number. So actually 2 is not a critical point. If it was a critical point, it'd be neither, right? Because it goes from decreasing to decreasing. But actually at x equals 2, this is technically not a critical point, again, because it's not in the domain of the function. So you don't have to worry about that one. But you do have to worry about x equals 4, right? So x equals 2 is the only thing that was not in the domain. Everything else we have to worry about. Okay, so at x equals 4, let's see, we have decreasing and then we have increasing. So therefore this is a local min. Is a local min. All right, so now we've classified our critical points, remembering that 2 is technically not a critical point. Okay, how about E? E, we want to figure out something about concavity, right? Where is it concave up? Where is it concave down? Where are there inflection points? This all has to do with the second derivative. So I'm going to be looking at the second derivative now. And again, we want to know when is it 0 and when is it undefined in order to break up our number line. So okay, again, I could ask, when is it undefined, right? When are you dividing by 0? And you would say at x equals 2. So at x equals 2, indeed, we are dividing by 0. So that's going to be one place where we need to break up our number line. And, okay, how do you make it equal to 0? Well, if you were to try, right? So if I was to go ahead and pull aside here and I was trying to set up 8 over x minus 2 quantity cubed is equal to 0, maybe the first thing you would do is multiply through by the denominator, and you would get 8 equals 0. Well, that doesn't work, right? There's no time when 8 is equal to 0, so that's saying that there's no way to make the second derivative equal to 0. So at x equals 2, that's the only place where we need to break up our number line. So let's go ahead and draw out our number line here. And we're going to break it up at 2. Remember, now we're plotting information about the second derivative because the second derivative tells us something about concavity, right? We want to know about concave up, concave down. So again, we're going to choose some test points, maybe like 0 and 3 or something like this, but you can choose, right, any test points that you want, so long as they're in the interval. Let's go ahead and plug these in, again, for the second derivative. So if I plug in 0 into the second derivative, I'm going to have 8 divided by 0 minus 2, that's going to be negative 2 cubed. So in the numerator I have positive, and in the denominator I have, let's see, a negative, 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 3 negatives, that's going to be negative. So I'm going to have positive divided by negative, that's going to be less than 0, and therefore we're going to have negative. What if I was to plug in something like 3? Well, again, in the numerator I'd still have 8, and in the denominator I'd have 3 minus 2, that's going to be 1 cubed. So that's just going to be, well, 8. And the big thing here is that it's positive, right? So here we have positive. Okay, so again, for part E, I'm kind of running out of room. Maybe I'll squeeze it in here at the very bottom of this page, right here. So F is concave up on 2 to infinity. F is concave down on negative infinity all the way up to 2. And then how about inflection points? Well, it does switch concavity at 2, but again, there's this word points, right? Whereas an inflection point. And if we go back to our definition of what is an inflection point, well, we realize that that value needs to be in the domain. It needs to be a point. It needs an x value and a y value. And if you were to try to figure out what is the y value corresponding with 2, well, again, you plug it into the function itself to get out the y value, and it's going to break, right? Because 2 is not in the domain. And so this is technically not an inflection point. So there are no inflection points. which is a technicality, I understand, but it's important, right? When we go to sketch this thing, we won't be able to draw a point there because 2 is not in the domain. All right, and now we're ready finally for part F. We have a lot of information. Let's go ahead and put it all together in a graph. So let's see here, draw out some axes. And it seems like something at least interesting is happening at 2. So at 2, something interesting is happening. We have a vertical asymptote, for instance. This is not in the domain, so let me maybe go ahead and use red here to signify a vertical asymptote. We're never going to cross this point. We also know that we have a slant asymptote, right? We have a slant asymptote at y equals x. So maybe if I was to go ahead and sketch something like this, we'll have a slant asymptote that will get closer and closer to this value as x goes to infinity or negative infinity. Okay, what else do we have? Let's see, we have Y-intercept at x equals 0, we get out the point -2. So let's go ahead and sketch this. So 2 down, there we go, -2, we include this point. We also know that it never crosses the x-axis, right? Never crosses the x-axis, that's interesting. So let's see, we've taken care of A, B, C. Okay, I think we're ready to start taking down some information about increasing, decreasing, concave up, concave down. So we need to break this up at 0, 2, and 4. So let's go ahead over here to 4. And now let's go ahead and break it up. So at 0, so I'm going to go ahead and draw a line here. At 2, draw a line here. And at 4, draw a line here. Now, when you're less than 0, we know that we're increasing. So less than 0, we have increasing over here. Between 0 and 2, we have decreasing. Between 2 and 4, we still have decreasing. And then 4 and bigger, we have increasing. Okay, and then finally for part E, it looks like we need to break it up just at 2. Before 2, it is concave down. So before 2, it's concave down, concave down, and then after 2, it switches to concave up. Concave up, concave up. So I just go ahead and write these out just so I have kind of all of the information on one graph here. And now we're going to go ahead and try to sketch it. Okay, so over here we have increasing and concave down. We need to end at this point here, and we have a slant asymptote. So we're going to be getting closer and closer to this as we go off to negative infinity. We are increasing, but concave down below its tangent line. So something like this. Okay, after this point we have decreasing and concave down. So it's decreasing, still concave down, and notice we have a vertical asymptote coming up. So it's going to be decreasing, concave down. It looks like it's going to be heading towards negative infinity here because it's decreasing and concave down. Okay, so something like this. Okay, now after the vertical asymptote, we wonder, does it come up like this or does it come down like this? So does it make this jump or whatnot? But it needs to be decreasing. So, okay, it can't come from down here because otherwise it'd be increasing. So it's got to be the top one. So it's decreasing and concave up. So decreasing and concave up. So, okay, something like this. Okay, decreasing, concave up, so it lies above its tangents. Okay, and then after that, increasing and concave up, and it needs to get closer and closer to this slant asymptote. So increasing, concave up, getting closer and closer to the slant asymptote here. So something like this maybe. So increasing and concave up. So we get a picture that looks like this, and notice that indeed it never crosses this x-axis, right? So this is another kind of piece of information that we had that we can verify now. Okay, and again, let's go ahead and use the Desmos to verify our answer. And so you can see I have it all ready for us actually here. X squared minus 2x plus 4 over x minus 2. And we can go ahead and plot some other things. For instance, x equals 2. That's where we had a vertical asymptote. And we also had a slant asymptote at y equals x. So we may want to plot that as well. And we can see that, yeah, the graph that we get on Desmos looks quite similar to the graph that we have. Also going through 0, -2 here. It never crosses the x-axis, so this actually looks pretty similar to what we have. So yeah, I am happy with our drawing here. Alright, so these were some long examples, a long video I know. Thanks for sticking it out, guys. I'll see you next time. Thanks.